Hey guys, welcome to day 19 of calculus. Next week is our last week of calculus, which I'm really looking forward to. We're going to talk about derivatives during that time, as well as some trig stuff to kind of get you going. That being said, today is our last major day of limit stuff. We will have a short quiz that will likely go out sometime tomorrow, probably, which you can work on all weekend. The goal is just to make sure that you're understanding the material and get you prepped for our post-test, which is coming up next week. So let's go ahead and get started. For today, we're going to be talking about a very unique concept. It is referred to as an infinite limit. Now, an infinite limit is the idea that as you approach an x value, your y value can trend towards a number that is infinitely large. In other words, you're looking at something referred to in algebra as an asymptote. An asymptote being in a case where you have on your graph a place where you are going towards infinity, at least in the upper axis or in the lower axis, so negative infinity. Now, for many of the problems tonight, there will be one set of limits, so we'll get some practice on that today. There will also be problems dealing specifically with the analytical approach, where you have to do it by canceling something. Now, let's talk about kind of the trends of how this looks and how this feels by looking at a graph and then by looking at the limit specifically. Okay? Let's get started. The first graph I want to look at is this graph, which is the example 3 over x minus 2. And the limit we're going to investigate is the limit as x approaches 2 from the right-hand side of this graph. Now, if we were going to do this by the numerical approach, we would make our table we're coming from the right-hand side, so 2 would go here. 2 is undefined when we try to plug it in, and so we want to approach 2 from the right. So this would be 2.1, 2.01, and 2.001. I'm going to save us some calculator work. I've already done these calculations. If you actually do the math, 2.1 is 30, 2.01 is 300, 2.001 is 3,000. And remember, you can keep getting closer by just moving this decimal place farther and farther along. So I could, in theory, also check numbers like 2.0001, in which case it has a number of 30,000. So what you can see is, as we're approaching from the right-hand side, we get close to 2, we have 30. Closer still, 300. Closer still, 3,000. Closer still, 30,000. So you can see that we're not approaching a specific number, we are approaching infinity. We would then therefore say that this limit is equal to positive infinity. Notice that we don't ever get infinity as an answer, we get a very large number and we tend towards that number, right? Each value that gets closer to 2 gets closer to infinity. And if we kept this trend going and did, a 2 with 4 zeros and then a 1, it get closer to infinity. A 2 with 5 zeros and a 1, we get closer to infinity. Each time we get closer to 2, we get closer to infinity. This is referred to in mathematics as an infinite limit. It is any limit, and note the word any here indicates that this could be from the left, from the right, or the general limit. Don't confuse it with plus and minus, this is from the left and from the right. So any limit whose value tends to negative infinity or positive infinity. So it is possible to have an infinite general limit. And we'll look at an example of what that looks like here in a second. It is possible to have an infinite limit that is just from the right, like we have here. It is possible to have an infinite limit that is just a limit from the left, as we have here. It depends upon the function, what you're going to be dealing with. For example, let's investigate a similar limit, approaching the same limit from the left. So again, we we would now look at values that are left of 2, and again, 2 is undefined. So there should be values like 1.9, 1.99, and 1.999. And again, I've already done the math for us. This would be negative 30, negative 300, and negative 3,000. You notice that each of these numbers gets increasingly larger in the negatives. So negative 30, negative 300, negative 3,000. If we kept this trend going, 1.999, 9, it'd be negative 30,000. And note the fact that these are negative 30,000, 3,000, 330, like the fact that these are all begin with a 3 doesn't matter. Like this could be negative 29, negative 407, negative 6,311. Like, they don't have to have a nice pattern. They often do. They don't have to have a nice pattern, though, to go towards infinity. And you can clearly see that no matter what, as we're looking through these numbers, we are clearly heading towards negative infinity. And so this limit would have a value of negative infinity. This happens whenever there's an asymptote in the graph. So let's actually look at the graph of this function and show how we can see this exact same thing play out graphically. Oh, come on, computer. Do it this way. So let's pull up Desmos. There's Desmos. Okay. Alright. So I have 3 divided by x minus 2. So I can see as I approach 2 from the right, we are heading towards infinity. It's an asymptote. I am clearly going upwards. And the closer I get to the value of 2, the farther up I end up going until I'm well off the page. And even if I zoom out, again, the closer my value gets to, you can track that number. You can see as the number gets closer to 2, I have to zoom out really far, but I will get in the thousands, in the millions, in the billions. I go up there. On the other side of this, as I approach 2 from the left, my number gets farther and farther negative. Notice how I can predict that by looking at the equation and doing it numerically. When I approach this thing numerically, I can clearly see my numbers get closer to infinity. I can clearly see my numbers get closer to negative infinity. I can see that because I can evaluate numbers that are close to 2, but notice I had to spot the pattern. Sorry. I had to spot the pattern. I had to keep seeing myself getting closer and closer to 2, and allowing myself to notice that pattern exists all the way through this function. This represents our infinite limits, and it's a big trend. Now, in this case, if I ask the question, what is the limit as x approaches 2 of this function, we would say it does not exist. Because remember, for a limit to exist, the left side and the right side have to agree. This one's infinity, this one's negative infinity, so this limit would not exist. Let's look at one where the limit does exist. In this case, let's look at the function as x approaches 1 from the left of 1 over x minus 1 squared, as x approaches 1 from the right of 1 over x minus 1 squared, and then the overall limit as x approaches 1 of 1 over x minus 1 squared. So these are 3 very different questions. Now again, I'm going to do it by the numerical approach. So, for this first one, I want to pick numbers that are to the left of 1. So there's 1. This would be 0.9, 0.99, 0.999. This one I'm going to go the other way because I'm looking for numbers to the right of 1. So here's my 1. And again, 1 is undefined. So this would be 1.1, 1.01, 1.02, 1.001. And let's actually plug this in and see what happens. So for these ones, I would get 0.01. No, I wouldn't. Let's see. I did the math earlier, and it's 100. There it is. It's 100, 10,000, and then a million. For these ones, it follows the same basic trend: 100, 10,000, and then a million. Okay. So we can clearly see that this one, as we approach it from the left, is going towards infinity. So this limit is infinity. As we approach it from the right, this limit would be infinity. We keep getting larger and larger values. And again, you notice there is a pattern, but the pattern is that it keeps getting bigger. Not that they all start with 1 and have zeros after them. It's the fact that this one's 100 and this one is 10,000. It's bigger. As we get closer to 1, our numbers get closer to infinity. Now, since these two agree, that means that this limit has to also be infinity. And we can see that if we actually look at the graph of this. Let's pull up this once again. And let's actually plug in that graph. So 1 divided by x minus 1. Excuse me. That's your lunch squared. So you can clearly see, as we approach our value of 1 here in the center, the left-hand side is getting more and more positive towards infinity. The right-hand side is getting positive towards infinity. And where are they going to meet in the middle? Infinity in this case. So you can clearly see, like, as we get closer and closer in value to a value of 1, it just keeps trending upwards to the hundreds and the thousands and the millions. But it keeps getting more and more closer to infinity. This is referred to as an infinite limit. And that's a big concept. It's one that needs to have these pieces fitting together. So, let's keep going. So now we've seen examples of how to determine if you have a limit analytically. We've also seen examples of how to determine it graphically if it's an infinite limit. So how do you do it if you want to do it... Oh, sorry. Scratch that, reverse it. We've seen examples where we did it numerically. We've seen examples where we do it via the graph. So how do you then do it analytically via the algebra? Well, it's actually pretty straightforward. Pull it up. You can determine if it's going to be an asymptote by just looking to see, where it ends up being 0 in the denominator. So if you have f of x over g of x, if g of x equals 0 at some value c, then there will be an asymptote at g. That's a big detail. It's that when the denominator equals 0, it's possible for there to be an asymptote. However, this is assuming that the top and bottom are in reduced form. If they are not in reduced form, you cannot determine when this is going to be the case. So, in order for this to work, g of x needs to be reduced. Using those properties that we had from Theorem 111, where we reduced the fraction down. So, you should be able to determine an asymptote readily by just looking at the denominator. Let's look at 3 examples. In all 3 of these examples, we're going to attempt to find the asymptote. So in the first one, my first equation is 1 over 2 x plus 1. My second equation is x squared plus 1 over x squared minus 1. And my third equation is going to be There we go. Okay, so this first one. So what we want to do, we want to make sure it's in reduced form first. Once we make sure it's in reduced form, we want to check when the denominator equals 0. So I look at this first one. Is it in reduced form? Yes. So now I take the denominator and set it equal to 0. Now I want to take this function, this new expression that I have, and solve it. So I divide both sides by 2, I get x plus 1 equals 0. Subtract 1 from both sides, I get x equals negative 1. This tells me there will be an asymptote at x equals negative 1. Note how simple this is, how straightforward it is. It always follows these same basic rules. No, I cannot tell you what the limit is this way. I can only tell you that it's going to either approach infinity or negative infinity, because those are the only options we had. Remember, this one would also match this property, right? But on one side it went to infinity, on the other side it went to negative infinity. You cannot usually tell this without needing more information. But you can at least tell it's either going to one or the other by using an asymptote. B, same thing. First we check, is it reduced? Well, I can factor a lot of this. X squared plus 1 doesn't actually factor, but the bottom does. X plus 1 and x minus 1. And since this doesn't factor and make it any simpler, I'm going to say that yes, this is reduced. Now, as I continue, I come here. I want to see where does the denominator equal 0. So I do the x plus 1 and x minus 1 is my denominator. I set the denominator equal to 0. Notice the numerator is not important because it is already reduced. So I look at the denominator now. I can then take this thing and split it into two problems. This is called the fundamental theorem of algebra. X plus 1 equals 0, and x minus 1 equals 0. And I can solve each one. For this first one I get negative 1. This one I get positive 1. So these are both places where there's going to be an asymptote. Now again, what I cannot determine is whether there's going to be a limit of infinity or negative infinity or neither. Because again, this does not tell me what kind of limit there's going to be. It tells me whether or not it's going towards infinity or negative infinity. In this case, these are either going to have limits of... So once you get to this point, what this implies is a mathematical symbol that says this is what you know as a result. That either the limit as x approaches 1 for this function, this tells me that it's either equal to infinity, negative infinity, or it does not exist. Which is important information. Again, it doesn't tell me which of these three is the possibility, but it does tell me that this is the possibility, right? Normally we get to a number, right? 4/3, 5/2, 7, right? We normally get a number. But in this case, just knowing this information is a big step forward. So there's my answer. I have an asymptote at x equals negative 1 and at x equals positive 1. Let's go up here. The reason why I stress reducing first is if you fail to reduce, you may end up getting extra answers. So here, I factor this. This becomes x plus 1 times x minus 1 over x plus 2, x plus 1. The reason why I say to reduce first is because if this happens, this will give me a new function, x minus 1 over x plus 2. This would tell me that negative 1 is a whole. It is removably discontinuous, as we talked about last time. Whereas at x equals negative 2, because again I set x plus 2 equal to 0. No, I only use the x plus 2 because I can cancel the other two after I've reduced. This one will be an asymptote. So again, reducing first is a big detail that can always help you. And this applies whether you're doing it from the left, from the right, or the overall limit. Is always reduce first if possible. This will be it for today. That's our last big piece. The big thing to note here is that in this case, you need to be able to determine when you would have an asymptote and you need to be able to evaluate limits. Those are the two big parts. So make sure you can take those steps. You have a relatively short homework assignment, only 8 problems. They're all limits, either one-sided or I think they're actually all one-sided limits. Do make sure, do not assume you're going to get an infinite limit. Do not assume you're going to get this material from today. It is simply not the case. The reason I've assigned the problems today is because there's a chance some of them have an infinite limit. There's also a chance they don't. Make sure to verify with your steps what it should say. You'll notice in the instructions when you get your assignment that it specifically says, if the limit exists, find it. Meaning it's possible it doesn't exist. It's possible it doesn't work. So take the time to find those pieces and use that information to better determine what we need to evaluate our limit. It's our last major day of just limits. Limits is like the first quarter of calculus, at least in my class. The second quarter is devoted to derivatives, which we'll talk about next. We'll only spend a couple of days on the derivative part of this, but it will be there. So make sure you can take these steps and find a solution. That'll be it for today. Hope you guys have a good weekend if I don't see you at the Zoom session tonight.